Welcome to today's class on functional analysis. Today we discuss unique Hand-Banach extensions. If Y is a dense subspace of a normed space X and G is a continuous linear functional on Y, then the uniform continuity of G enables us to conclude that G has a unique continuous linear extension F to X and also that norm F equal to norm G. Thus, G has a unique Hand-Banach extension to X if Y is dense subspace of a normed space X. If, however, Y is not a dense subspace of X, a Hand-Banach extension to G of X may not be unique in general. So we are going to form a characterization for existence of unique Hand-Banach extensions. Normed space which admit unique Hand-Banach extension can be characterized in terms of the geometry of unit poles of their duals. So it is discussed in the following theorem. Theorem by Taylor and Fogel. Theorem is this: let X be a normed space for every subspace Y of X and to every G in Y dual. There is a unique Hand-Banach extension of G to X if and only if X dual is strictly convex. That is, for F1 not equal to F2 in X dual with the norm F1 equal to 1 equal to norm F2, we have norm of F1 plus F2 less than 2. So that is the condition for strict convexity. So we prove this theorem. First, assume that X is strictly convex. We are going to show that the extension is unique. So proof. Assume that X dual is strictly convex. Let Y be a subspace of X and G belongs to Y dual. Let F1 and F2 be Hand-Banach extensions of G to X. Now, if G is 0 on Y, then norm F1 equal to norm G, that is equal to norm F2, and since G is 0, this is equal to 0. So the same implies norm F1 equal to norm F2 equal to 0. So this implies F1 equal to F2, that is equal to 0. So in this case, the extension is unique. Now let G not equal to 0. Assume that norm G equal to 1. Without loss of generality, we can assume that norm G equal to 1. Now since F1 and F2 are Hand-Banach extensions of G to X, we have F1 plus F2 by 2 is a continuous linear extension of G to X, and therefore norm of F1 plus F2 divided by 2 is norm G, that is equal to 1. So this implies norm of F1 plus F2, this is equal to 2 into 1, taking this 2 to this side, so this is equal to 2, that is norm F1 plus F2 equal to 2. Take this as equation 1. Now since norm F1 equal to norm F2 equal to norm G, that is equal to 1, by strict convexity of X12, we have norm of f1 plus f2 is less than 2, because norm f1 and norm f2 equal to 1, and by definition of strict convexity, which is a contradiction to 1. Therefore, we must have f1 equal to f2. That is, the Hand-Banach extension of G to X is unique. So this proves one part. Now we prove the converse. Conversely, assume that X dual is not strictly convex. Then there are f1 and f2 in X dual such that norm f1 equal to 1, norm f2 equal to 1, and norm f1 plus f2 is equal to 2, since X dual is not strictly convex. Let xn be a sequence in X such that norm xn equal to 1 for each n, and modulus of f1 of xn plus f2 of xn converges to 2. This is possible by choice of f1 and f2. Now by parallelogram law, for elements of K, we have modulus of f1 of xn plus f2 of xn whole square plus modulus of f1 of xn minus f2 of xn whole square. This is equal to 2 times modulus of f1 of xn square plus 2 times modulus of f2 of xn square. Take this as equation star. Now since norm of f1 is equal to 1 and norm of f2 equal to 1, we have modulus of f1 of xn is less than or equal to 1 and modulus of f2 of xn is less than or equal to 1, since norm of f1 is supremum of modulus of f1 of x such that norm of x less than or equal to 1, and norm of f2 equal to supremum modulus of f2 of x such that norm of x is less than or equal to 1. Therefore, this quantity modulus of f1 of xn and modulus of f2 of xn will be less than or equal to 1. Therefore, 2 times modulus of f1 of xn whole square plus 2 times modulus of f2 of xn the whole square. This is less than or equal to 2 into 1 plus 2 into 1. So this is 4. That is, LHS of star is less than or equal to 4. Now, since by choice of f1 of xn and f2 of xn, modulus of f1 of xn plus f2 of xn converges to 2. This is by this choice. So this implies modulus of f1 of xn plus f2 of xn the whole square tends to 4. That is, first term of equation star is tending to 4. Therefore, first term of star tends to 4 as n tends to infinity. So how this term is tending to 4 and this is less than or equal to 4. Therefore, the second term of RHS of star tends to 0. That is, modulus of f1 of x minus f2 of x tends to 0. And modulus of f1 of xn tends to 1 and modulus of f2 of xn tends to 1. Now let y equal to set of all x in x such that f1 of x equal to f2 of x, and define g belongs to y dual by g is equal to f1 restricted to y and that is equal to f2 restricted to y. So from this you can see that f1 and f2 are extensions of g to x. We show that norm g equal to 1. Now since norm g is norm of f1 restricted to y and this is less than or equal to norm f1 and that is equal to 1. Therefore, norm g is less than or equal to 1. Now we prove the other inequality. Consider a in x such that f1 of a not equal to f2 of a. And for n equal to 1, 2, etc., let Zn equal to xn minus f1 of xn minus f2 of xn divided by f1 of a minus f2 of a into a. Then f1 of Zn equal to f1 of xn minus f1 of xn minus f2 of xn divided by f1 of a minus f2 of a into f1 of a. So this is equal to f1 of xn into f1 of a minus f2 of a minus f1 of xn minus f2 of xn into f1 of a divided by f1 of a minus f2 of a. So this is equal to f1 of xn into f1 of a minus f1 of xn into f2 of a minus f1 of xn into f1 of a plus f2 of xn into f1 of a divided by f1 of a minus f2 of a. So you can cancel these two terms. This is equal to f2 of xn into f1 of a minus f1 of xn into f2 of a divided by f1 of a minus f2 of a. So that is equal to f2 of xn into f1 of a. You add and subtract f2 of xn into f2 of a minus f2 of xn into f2 of a minus f1 of xn into f2 of a plus f2 of xn into f2 of a all divided by f1 of a minus f2 of a. So this is equal to, you can take f2 of xn common here, f2 of xn into f1 of a minus f2 of a minus, you can take f2 of a common here, minus of f1 of xn minus f2 of xn into f2 of a divided by f1 of a minus f2 of a. So that is equal to f2 of xn minus f1 of xn minus f2 of xn divided by f1 of a minus f2 of a into f2 of a. So that is equal to f2 of xn minus f1 of xn minus f2 of xn divided by f1 of a minus f2 of a into a. So this is f2 of Zn. So we have started from f1 of Zn. So we have reached f2 of Zn. Therefore, f1 of Zn equal to f2 of Zn. So you know that f1 equal to f2 on y. So this implies Zn belongs to y. For each n. Now since modulus of f1 of xn minus f2 of xn tends to 0 as n tends to infinity, we have f1 of xn minus f2 of xn tends to 0 as n tends to infinity. Now since Zn equal to xn minus f1 of xn minus f2 of xn divided by f1 of a minus f2 of a into a, and this quantity tends to 0, and f1 of xn minus f2 of xn tends to 0 as n tends to infinity implies Zn tends to xn from this. So this implies Zn minus xn tends to 0. All this happens from this as n tends to infinity. Therefore, norm of Zn minus xn tends to 0 as n tends to infinity, and since norm of xn equal to 1, we must have norm of Zn equal to 1. Also we have f1 of Zn equal to f1 of xn minus f1 of xn minus f2 of xn divided by f1 of a minus f2 of a into f1 of a. And we have f1 of xn minus f2 of xn tends to 0. So this quantity tends to 0. Therefore, f1 of zn converges to f1 of xn. So since f1 of xn minus f2 of xn converges to 0 as n tends to infinity, we have f1 of zn converges to f1 of xn as n tends to infinity. So this implies f1 of zn minus f1 of xn converges to 0 as n tends to infinity. Therefore, modulus of f1 of zn minus f1 of xn converges to 0. And as modulus of f1 of xn is converging to 1, we must have modulus of f1 of zn converges to 1. Now for large n, let yn equal to Zn by norm Zn, then yn belongs to y. Since Zn belongs to y and y is a subspace, since y is a subspace, and Zn belongs to y. So yn belongs to y, and you know norm Zn is in K. And norm yn is norm Zn divided by norm Zn. So this is 1. And since yn belongs to y and g is equal to f1 restricted to y, implies modulus of g of yn equal to modulus of f1 of yn, because on y g is equal to f1. Therefore, modulus of g of yn equal to modulus of f1 of yn, that is equal to modulus of f1 of yn is Zn by norm Zn, so this is equal to 1 by norm Zn into modulus of f1 of Zn, and this tends to 1. This is since modulus of f1 of Zn tends to 1 and norm of Zn equal to 1. That is, modulus of g of yn tends to 1 as n tends to infinity. So this proves the reverse inequality. Therefore, norm g equal to 1 as n tends to infinity. Thus, f1 and f2 are two distinct Handbanach extensions of G to X. So this proves the theorem. That's all for the day. Have a nice day.